Hey guys, welcome back. In the last video, we started talking about oscillations, and we looked at this GIF in the top right portion of the graph, where it was the time domain, and we kind of looked at mass on a spring oscillating back and forth, and how we could represent that, as well as a pendulum. In this video, we're going to start talking about the space domain, and then we're going to combine the two. So looking at this graph once again, it looks similar to what we went over last time, only if you notice, we're plotting this with respect to x, our position. So instead of being time dependent, it's going to be dependent on the location we look at. And so our y-axis is going to be our y of x. It's our y values telling us how far we are from equilibrium. So if something's oscillating back and forth, we're going to some amplitude and coming back to equilibrium, and that's what this x value is going to tell us. And so the main takeaway when we start talking about this, there's not very many interesting things we could talk about. This is something that you would have gone over in your math class. We're just going to add a couple of Greek letters to it. And so looking at this wave, we see that we have a repeating pattern. We're starting at our equilibrium, we're coming up, and we're coming back down, and then we're coming back to equilibrium, and then we're starting over, and we have this repeating wave pattern. And so since this is position, this is actually a measurement of length, how long this wave is, we're going to refer to our distance of each cycle that we go through as our wavelength, how long this wave that's we're looking at is. And so before we came up with a relationship for our position with respect to time with a trig function, and we had to scale it, and we saw that we scaled that with our 2 pi over our period, and then we would have multiplied by time. And so what we see here is something very similar. We're going to need to scale this and be able to represent how the position of this wave, only instead of being time dependent, it's going to be dependent on x. And so if we do the same thing we did before, is when x equals our wavelength, we're going to multiply that by 2 pi because we're working in radians. 2 pi radians would be one cycle. So our factor that we're going to scale by is 2 pi over our wavelength this time. And then out here, it's going to, our trig function and our sine, as you see here, we have a negative cosine. It just has to do with how I drew this. So I put our y-axis where we're at our minimum amplitude, our negative amplitude. So at our x equals 0, we want to be at negative a. So at x equals 0, cosine is going to equal 1, and we'll just have that negative a. And of course, that's going to change depending on what we're working with. And the next slide, you'll see that this is going to change. I believe it's a sine. I don't remember. But what the main takeaway from this is our this k value equals 2 pi over lambda is what we're working with. Before, we saw that we represented our 2 pi over our period as our angular frequency, but here we're going to represent 2 pi over lambda as k, and that's known as the wave number. And so there's not really much to talk about here until we combine our position and our time together, because once again, this is just looking at some sinusoidal wave, and it should be pretty familiar to you that this is how we represent them. So now if we imagine that wave that has some position from equilibrium depending where we're at along the x-axis, so we could think of our hanging mass on a spring, we just had a mass going up and down. But if we think of a long train of these hanging masses, we could see that they're going to be oscillating up and down, but it's also going to depend where we look at which hanging mass. If we imagine these are different hanging masses creating this wave, it's going to also matter at what time we look at that, because they're oscillating up and down, and they're all going to be in different positions. So the first thing we could come up with is, because now we have our wave is moving, as imagine this is this red line is going to be moving to the right. We need to be able to come up with a wave velocity. So by definition, frequency is how often we move forward a distance lambda, which is just our wavelength. And what we see is, if we multiply lambda and our frequency together, well, lambda is just measurement of meters, and frequencies per seconds, 1 over seconds. So when we multiply these two things together, we get velocity, which should make sense, because all it's saying is how long it takes this first wavelength to move over into position of the second wavelength, which would just be a distance over some amount of time, which is our velocity. And so we could combine these two concepts that we came up with, our position with respect to time, and our position from equilibrium with respect to our position, if that makes sense. So we're looking along our x-axis is our position that we're interested in, and then our y, x of t, would be our how far we are from equilibrium, our displacement. So what we're going to do is the same thing. We're just going to take these. Obviously, we first need to look at our trig function to pick out which one we want to use. And in this one, I have drawn it as a normal sine function, so we could just choose sine as our trig function. And as before in both problems, we just multiplied by our amplitude, which should make sense, because whenever our trig function equals 1, we want to be at our amplitude. And so here, if we just pretend time isn't, if we hold time still, we get that same equation we saw on that previous slide. And then if we hold our position still, we look at our origin. This term becomes 0, and we're just left with the negative 2 pi over our period times t, which is what we saw in the previous video. Well, this negative sign sometimes can be confusing to people, but what it shows us is, if we look at our origin, and as we're assuming that our wave is traveling to the right, as our wave travels to the right, our wave here is going to be crossing our origin. So it appears, looking at this plate, or when we look at this wave, it is moving to the right, and it first seems like it should be a positive value, but what's happening is we're looking at one position and we're actually going backwards with respect to the origin. So that's where this negative value comes from. If our wave was going to the left, our negative would become a positive. And so we could substitute these two, our coefficient in front of our variables, and plug in our wave number, because it's just 2 pi over lambda, and we could plug in omega, our angular frequency, to represent 2 pi over t. And so this is the general equation for position of a wave from our position from equilibrium with respect to position and time. So if we take a look at this GIF, we can see that there's actually two different types of traveling waves. We got a transverse wave and a longitudinal wave. And the only difference between these two is the direction of our displacement from equilibrium. So we see both waves are traveling to the right. The transverse wave, though, our displacement is perpendicular to the direction of travel. And this would be like a guitar string, or just a wave on any string, really. Or maybe waves from an earthquake would be transverse waves. And then if the bottom, the longitudinal wave, is the displacement from equilibrium is in the same direction of travel. And we'll talk about that more in our next video, which will be our last video. where our displacement from equilibrium is in the same direction. But we could represent both of them using the same equation from the previous slide. And one important characteristic of these waves, as we've seen with other things that we've talked about in the class, is that it follows the superposition principle, which tells us that we could represent a wave 1 plus wave 2 as just some third wave. And what that means is if we have a wave 1 I've drawn here and wave 2, if we add those together, we're going to see, because these waves are in the same phase, we see that they add, which is known as constructive interference. It's the sum of these two waves. And then on the right side here, I have these two waves drawn opposite of each other. So this is a sine function, this is a negative sine function, and what we see is when we add these two together, we have a flat line. They cancel each other out. Our max amplitudes here is our negative amplitude here, and vice versa here, where these are both following the same position. So we see that we just get amplitude of 2a for the one that's constructive interference in this example, and we just have 0 amplitude throughout this entire graph. And so if these waves are traveling waves that are interfering with each other, in this example we have they're similar waves, but they're traveling opposite directions. And you could see how the superposition principle plays out, as each peak, if they're in phase with each other, adds to an amplitude that's twice as high of either one of these. And then when our negative amplitude and our maximum amplitude are together, we see that our wave down here, this is the sum of these two waves, is going to 0, and it keeps oscillating back and forth like that. And so if you look at the position where the bottom wave is crossing the equilibrium, you'll notice that there's spots that aren't moving ever. They're constantly at equilibrium as these two waves are added together. And so this is an important concept that we'll talk about in a second, but these positions where we're crossing our equilibrium spot and it's continuously staying at equilibrium, certain points, are called nodes. And our position where we're going from oscillating is our antinodes. Where our position actually reaches a maximum amplitude is an antinode, and where we have no movement at all is called a node. And so if we think of a wave on a string, if we send a pulse in the string, we see that it comes in, it runs into this where the string's attached to the wall, and then reflects back upside down. So in that previous GIF, we saw that we had these waves traveling opposite directions, and we saw that we had these nodes and antinodes. And so we could think of this as if we had, instead of just having a pulse coming in on the string and reflecting back off, if we continuously oscillated this string, we would have a wave coming to the right and then a wave reflecting off and coming back to the left. And so what we end up seeing is we change the frequency, we oscillate this string. If we think of this as the string coming in, that pulse we saw in that GIF coming in, it's going to reflect back and come back towards the left. So if this is a vibrating string, we'll see that we have the shape of our wave coming in and our wave coming out. And so depending on the frequency of our wave, we're going to see a different amount of nodes and antinodes, because frequency is dependent on our wavelength, and velocity. And so what we see for a wave on a string is our velocity is dependent on our F, this is our tension of the string, and mu is our line density, our linear density of the string. So it's kilograms per per meter. And then F, I'm using F because we're already using T for the period to not confuse anyone. But this is just our tension in the string. So that's just how hard it's being pulled. And we'll work an example that will demonstrate that. But here, let's take a look and kind of come up with a formula to figure out what frequency these strings would have to vibrate given some length of the string. So all we need to do is think about how what length our wavelength could be, given that we know our two positions are where those strings connected. So let's just pretend this is either side of a guitar. We know that those spots aren't going to move because the string is being held there. So we're only able to see these standing waves given a certain frequency because we know that our wavelength is dependent on that frequency. So here we see that if we only look at one of these, this is only half of a wave, right? We're only starting at the equilibrium point. We're coming up and we're coming back down, but then it stops there and our reflection comes back. So this wavelength is going to be 2 times the length of the string. And if that seems a little confusing, this next example is a little more obvious because we have one full wavelength. It should be pretty apparent. We have a wavelength right here, and our wavelength is going to be length L. And so if we look at how many nodes and antinodes we have, well, we have our 2 nodes from where it's held together here in our first example and just one antinode. Well, now in this example, this standing wave, we have a node at either wall as we did in the first one, but now we have this node in the center. And I didn't draw it, but I should have drawn a, to make this look kind of like an infinity sign, a wave of the reflection. So this is only the wave going into the wall. I forgot to draw the reflection, but pretend that each of these has 2 of these shapes here and here. And same with the following examples. But we see that as we increase our frequency, we're going to get more nodes. And so our standing wave are waves that fit within our length depending on I guess what I'm trying to say is that our wavelength, it could only be in certain increments, because we can't have, in this example, we can't have 1 1/5 wave because our nodes at the endpoints wouldn't be nodes. Our endpoints wouldn't be nodes. So to get a standing wave, our wavelength needs to be in an increment of our wavelength. So we started with a half a wavelength was the length of our string. Here, our wavelength is the wavelength of a string. And so if we go on, we'll see that once we add another half wavelength, we'll get 3/2 L. And then if we add, well, here we have at the bottom, we have 2 full wavelengths. So our wavelength is half of our length. And so applying that to our V equals F lambda, we see that we have a dependency on what frequencies we could have with respect to n if we let n be our antinode. So those lowercase n is just really how many antinodes we have on the string. And so what we could say is that we have some frequencies that's dependent on how many antinodes we have. And we'll see here applying that n is just how many antinodes we have. And that's going to be dependent on the velocity divided by 2L. Or we could substitute velocity as our square root of our tension divided by our linear density. So at this point, if you're wondering what I'm talking about, hopefully this example will clear things up a little bit. I know it's a lot of new information, but it's relatively straightforward. We've worked with waves in the past. So let's say that we have a example here is if a string is a length of 1.5 meters is plucked to generate a frequency. So once again, we could think of this kind of as a guitar string. And the frequency is 222 hertz. What is the mass m? So we basically are creating some tension in the string by having a mass hanging over a pulley, which we've done before. So what is the mass m of the hanging object if the string has a linear density of 1.2 times 10 to the negative 3 kilograms per meter? So that's just basically how much this string weighs per each meter. Well, in this last slide, we know if we have a standing wave, a wave that fits perfectly within this area, the length of our string is known as a standing wave. We have a frequency dependency on how many antinodes we have, that's equal to n over 2L, and then square root of f over mu, which is just our velocity, representation of our velocity. So we don't know our tension in this problem. That's what we're going to end up having to solve for, because our tension in this case is just going to be our hanging mass times gravity is causing the tension in this string, and then mu we're given. So we could represent and substitute our F for tension. It is equivalent to mass times gravity. And if we look at this string, we have 1, 2, 3 antinodes. So our n value is just going to be 3. So if we plug all this in, we're going to get the frequency that this is vibrating at to create our 3 antinodes, which we're told is 222. And we'll end up with this. So doing a little math, we're just going to divide over 3/2 L, and we'll take the square of both sides to get rid of the square root. And then all we need to do is multiply both sides by mu and divide by gravity. And we see that our mass is equal to what's written here. So now we know all the values, and we could plug that into our equation. And we end up with a hanging mass of 6.03 kilograms. So what this tells us is if we want to have a frequency of 222 hertz, that creates a situation where we have 3 antinodes, so basically 1.5 wavelengths vibrating on the string. We would have to create a tension in this string of 6.03 kilograms times gravity, and then that's also dependent on our mu. So we're going to work some more problems in the next video that will cover sound. There's not really much else to talk about in this situation that's interesting, but we'll cover a little more if you're a little confused still about standing waves and oscillations.